All right, hello, and welcome to the second week of NTI. We are looking at the definite integral as a function. So, first, it's important to understand where we came from. So, we looked at the integral of a function from a to b bound by those two things, and we know this as the area under the curve. However, from before, we looked at a function and we put a little apostrophe on the f that represents the function, and we know that this means the slope of the function. Here, what is really our star, or we're highlighting the fact that capital F of x is the definite integral function. So the area under the curve is now represented with capital F of x. So our capital F of x function actually accumulates area as we go from 0 to x. This function is not graphed. The function that we're accumulating area on f of x, or f of t, because it's the same, is graphed at our right. And I put a little bookworm there, and it's dressed like a honeybee for some reason, but I thought it was really cute. So this guy is telling us to find the accumulating area on the function. So I went ahead and marked out the area of each section. So per unit, I marked out the area. And you can do this ahead of time if you want, before you get into the examples. But that accumulation of area is going to fit into the chart down here. So if we start off with 0 and we accumulate area to x, and I want to accumulate area all the way to 0, then I'm not going to get any area accumulated. I'm not going to accumulate any snow. So looking at 1, if I accumulate all the way till x equals 1, let's say maybe this is time after an hour. After an hour of snow, we've accumulated we've accumulated 2 inches of snow, because that's the area between 0 and 1. We'll accumulate 3 more inches from 1 to 2, and we'll have 5 inches of snow accumulated, maybe on our nice lovely porch in the middle of this month here. Hopefully not, that would be pretty disgusting. And then we keep on going, and we add all this area that's above the x-axis, and we'll actually subtract area that's below the x-axis. That's why from 4, really from 3 to 5, we are subtracting area to get these answers. And we add more area from 5 to 6.5 because it's above the x-axis, and you can see that comparison there. So that's why I've added these minus, minus, plus, plus, minus, minus. So that's not too bad. Those are the answers there. Now, the derivative of capital F, or the accumulation function, is a little bit strange, but that's just the original y values. So since capital F of x is an integral, if we were to take the derivative of capital F of x, the derivative of an integral, we would end up with the original function. That's why we have this statement over here on our right. So this chart isn't so bad to fill out because it's just asking us to take the derivative of capital F of x. And we see it in a few different ways of marking the notation. So what's the y value of the function at x equals 0? That's 1. What's the y value of the function at x equals 4? That's negative 4 right here. What's the y value at 6.5? That's 0. So that's telling us the derivative of the integral. So we're just looking at the notation with these first two examples, knowing how to look at them. Now here with this second example, I've got my area marked out again, and I've marked out my quarter of a circle area as pi, and -2. What's strange about this down here, I have negative area in this trapezoid right here. As I carefully highlight this, I've got negative area in the trapezoid. That's because I'm starting at 0. I'm starting at this bottom bound, and I'm moving backwards to -2.5, where my trapezoid ends. So the area that I accumulate in a negative direction on a positive y value is going to be negative, or with positive y values is going to be negative. The area that I accumulate with a negative direction and negative y values, that's going to be positive area. So that's why I've marked them as +1 and +1.5, and then -3.5 as my total area for this trapezoid. Here, I've written out my work for this section. The toughest question on here for A through H is probably going to be something like D. If you're adding the total area of something from 0 to 6, so we're actually integrating from 0 to 6. That's what capital F of 6 means. I'm going to actually add the semicircle. Whoa, I'm adding the semicircle and the small triangle that's below the x-axis here together. So that's why I have 2 pi minus 2. So make sure when you're adding large sections that you include the area that's already happened before, and you just add those together. For H, it's the same way. I added the yellow triangle that was 1.5 with the large trapezoid that was -3.5. And you notice I just canceled out the middle area, so all I was really adding together was -3 and 1. So I get -2. Now things get a little fishy down with I. Not too bad, actually. It's just the y values. So what's the y value at, say, at 5? Well, that's going to be -1, because remember, that's just the derivative of the integral, which is the original function's y values. But when I look at the second derivative of capital F, remember that the first derivative of capital F is the y values. Well, if I take the second derivative of capital F, that's the original function's slope, like we used to work with the derivative. So the slope of the original function is the derivative. So what's the slope of the function at 2? So I'll go to 2, and I'll remark this line up here. That's a slope of 0 at x equals 2. So my slope is 0. The second derivative of capital F at 2 is 0. The second derivative of capital F at 5, here's 5. That slope is -1, down 1, right 1. Second derivative of -0.5, -0.5, that's in here. -0.5 is right there. The slope of that line is -2 2 positive over positive 1, so negative 2. And then, oh boy, they almost got us. There's no slope at this cusp. There's no slope there at the cusp. Tricky, tricky Cyclops. So make sure you're careful with your slope, with your idea of slope. And then the last thing I have to show you is on what subintervals for the entire graph from -4 to 6 is f increasing or decreasing. So this is increasing, or a function is increasing if the first derivative is positive of it. Now we're taking the first derivative of capital F, but we were told since the very beginning that the derivative of capital F is undoing an integral. So we just end up with the function's y values. Same thing if we're decreasing. We'll just take the derivative of capital F and we'll find when the y values are negative. So the function's y values are positive from -2.5 to 0, right? Yes. And from 0 to 4. 0 to 4. There we go. So that means the function is increasing on these intervals. And the same logic applies to decreasing. It's decreasing from -4 to -2.5 and 4 to 6 because the y values are negative. So as long as we've connected those ideas with what we already talked about in the class on what the first derivative of a function means, we can get that. Here is an example I'd like you to try out. And then there's also this super secret challenge game that I'd like you to try and complete for this week. I'll also post on Google Classroom this image and give you the quizzes assignment to complete. It's just one assignment as well. So thanks for watching, and I'll talk to you guys this week. See ya.